Hi, today we will talk about induction machines after the synchronous machines. So induction machines working on a really simple principle, and first I would like to show you a couple of videos to discuss this. Okay, the principle, as we have seen from the first semester, is basically Lenz's law and eddy current. So Lenz's law states whenever you have a variable magnetic field in a conductor, that will induce some currents, and we have seen it in some applications like eddy current breaks in the first semester. So here basically you have just copper and magnet, and normally magnet doesn't attract to the copper, but if you just happen to drop it over the copper, as it moves along the copper, it induces some alternating magnetic field, and those induces some currents in the copper, and those circulating currents, eddy currents induced in the copper, actually opposes the movement of the magnet, so it slows down the drop of magnet. Okay, so then let's see what happens if we rotate a magnet over an aluminum disc. So here we have a magnet over an aluminum disc, and that guy is rotating it over the aluminum disc. So normally there's no attraction between aluminum and magnet, but once you rotate it, then the aluminum starts rotating, and this is the basic idea of an induction machine. Okay, so what he's going to do now, I think now he's going to do it faster, using some electric drill, and it just starts rotating it. Again, I would like to emphasize there is no attraction between the aluminum and magnet, so it's not rotating by attraction, but it is rotating due to induced currents, electric currents in the aluminum, and those induced electric currents are interfering with the magnetic field. We have seen it with the synchronous machines in the first weeks. So we were applying a rotating MMF with 3-phase, and with the help of that rotating MMF, I will be able to generate some rotation. So here you see a simple example. So actually we have the same setup in our lab. So there's a Coca-Cola tin, aluminum tin, and on the rotor, on the stator, we have a 3-phase winding, so it is just creating some rotating MMF. And when you put just aluminum can into the stator, what you will see is a rotation like that. Actually, I wish once you are back at the university, you will see a demonstration of that thing in our lab. So it's just rotating, and this is the main idea of induction motor. So actually induction motors, they are invented by Nikola Tesla and Galileo Ferraris, and actually there's a debate between like who invented it first. It seems like both of them invented it independently, so you can have a look at their patents, and also there's a case explaining the invention process. Anyway, so in the below you see the original patent from Nikola Tesla from 1889. So at the end of the day, we have the rotating MMF generated by a 3-phase winding. Okay, so that is the exactly same as the synchronous machine. So the synchronous machine stator and the induction motor, the stator, they are exactly same. So we have a rotating MMF. But in the rotor, they are quite different. So induction motors are actually really popular in industry because they have many advantages over synchronous machines. First of all, they are really robust and simple. So they have no permanent magnets, no field windings or brushes, as we will see as the synchronous machine. So having no electrical brushes in the Rotor means, there's no mechanical abrasion or there's no requirements of maintenance, and you don't need any expensive magnets in the rotor. So actually it helps to reduce the costs. So I mean, at the end of the day, like over 90% of the motor used in industry are using induction motors. Okay, and actually, if you think about it, you know, actually I think half of, think all the hydro generators, all the wind turbines, all the solar energy, nuclear energy, all the energy that we generate, I think over 60% of the all electrical energy, generated by humans are consumed on induction motors. And actually Tesla uses induction motors in a couple of their models. I think Model S uses induction motors, and actually I'm not opening it, but I strongly advise you to have a look at those manufacturing videos before proceeding. So on the stator side, we have the three-phase, we can have double layer or single layer distributed winding. Again, we didn't covered in detail of those topics yet, but what you should know at this stage is, induction motors are excited with balanced three-phase AC currents, similar to synchronous machines. But on the rotor side, maybe we have two different types of induction motors. The first one is the wound rotor. Okay, so it has a three-phase winding similar to the stator, but terminals are carried out with slip rings, so different from the synchronous machines. In the synchronous machines, remember, we were having some electromagnets or permanent magnets in the rotor, so those permanent magnets or the electromagnets are locking with the rotating MMF, and they were rotating at the same speed, they were rotating at the synchronous speed. But in the induction motor, there's always some difference in those speeds, so that's why they are also called asynchronous motors. Anyway, with the wound rotor, again, we don't have just two terminals coming out of the rotor, but it's just another three-phase winding, so you can see three windings coming out of the rotor. But this type of wound rotor is not that common. The most common type of the induction motors are called the squirrel cage induction motors. So they are basically short-circuited aluminum bars, so there is no slip rings, nothing. Okay, so squirrel cage rotor is also called, like, where squirrels or hamster used to run, is like over a wheel that they can rotate. Anyway, so if you look inside of a squirrel cage induction motor, first have a look at on the right. So they have those bars, so those bars are aluminum bars, and those aluminum bars are short-circuited using end rings. So on the right and on the left there are two rings, they are short-circuiting those two coils. So electrically, if you look at that picture, it is the same as an Coca-Cola tin. Okay, so it is short-circuited. So whenever you have, for example, between those bars, whenever you have varying magnetic field, that will induce some voltage, and that induced voltage will create some current to flow those bars, and the shape is optimized to maximize the torque. Normally we cover that in the master's level in the design of electrical machines. So once you have the thing on the right, okay, so in order to maximize the field, I mean, you can technically rotate it like that, as we have seen in the Coca-Cola motor, but what you can do is you can put some iron magnetic steel laminations around those bars to reduce the reluctance and increase the inductance, so it will increase the performance of the induction motor. Again, please have a look at those two video links at the below if you want to have a physical understanding of how those machines are manufactured. Anyway, so the rotor in this type of induction motors, and those are really the most popular type. So in these ones there is no coppers, there's no brushes that is coming out of the rotor, so it is just a closed box, so you don't have any mechanical or electrical contacts between the rotor. So that is why they are really robust and reliable. So that's the main reason why they are really popular in industry. So before proceeding on, again in the next week we will see the equivalent circuit, but let's start with some definitions. So first, as we have seen in the early weeks, so there's the synchronous speed. So synchronous speed definition is the same with the synchronous machine. So synchronous speed is the speed that is rotating with the MMF. It can be electrical or mechanical, but it is the speed of the stator excitation. So first we have the electrical speed. And electrical speed, if the stator is excited with electrical frequency, let's set 50 Hertz. Again, you can have a 50 Hertz electrical speed, but most of the case it is defined as radians per second, so it is 2 pi fs. Okay, then you can have the mechanical synchronous speed, and again we have the same definitions in this as in the synchronous machine as the number of poles. So you need to divide the electrical frequency by the pole pairs. Okay, so you divide the electrical speed by pole pairs, or pole number divided by 2, so you have the expression on the right. Or you can write that thing in mechanical speed. Usually instead of radian per seconds in mechanical systems, RPMs are commonly used, so you can write that thing in RPM. Okay, so that was, again, we derived it in the previous weeks, and if you divide it by 60 on the left, so you can have the fs as the frequency. So if you just multiply fs by 60, you have 60 fs, so that is the electrical revolutions per minute, and you divide it by pole pair, or divide it by p over 2, so it is 60 fs divided by p over 2, that is equal to 120 times fs divided by pole pairs. Okay, so again, if you have a two-pole machine, then the synchronous mechanical speed for a 50 Hz system is 300 rpm, or if you have a four-pole system, then the synchronous speed in mechanical side is 1500 rpm. Okay, then the most important definition for the induction motors is slip. Okay, in Turkish is kayma. So slip is the difference between the rotor speed and the stator speed in per unit, or in normalized terms. So in technical definition, it is omega s minus omega r being the rotor speed, the rotor rotational speed, divided by omega s. So what does it mean? So, or you can write the same thing in terms of the RPM. So it is ns. Ns is the rotational synchronous speed in RPM, and R is the rotor speed in RPM. So the difference between these two divided by, or normalized with respect to per unit system, by ns. So I will give you a couple of examples and it will be more clear. So if slip is 1, so that means there is no rotation at all. So in order to have slip is equal to 1, nr should be 0. So when slip is equal 1, so it means like your for example, your car is stuck in a snowy day, so your wheels are spinning, so your MMF is rotating, but your car is not moving at all, so they are not having any mechanical rotation. So that is, you have 100% slip. So that means, in our induction motor, you will have S is equal to 1, slip is equal to 1 when the rotor is not rotating, nr is equal to 0. Okay, And if there is no slip, then that means rotor is rotating at the same speed with the synchronous speed. Nr is equal to ns. So let me go back. So if nr is equal to ns, or omega s, or omega s is equal to omega r, then you will have zero slip. Okay, but if you have zero slip, so that means you are rotating. For example, think of that video that's holding the magnet. So you are rotating the magnet, but the aluminum disc is rotating exactly the same speed with that magnet. So from the aluminum's perspective, so the magnets are not moving. So if it is not moving, so it is as if it's not creating any varying magnetic field. So that is, really important. So the induction motors cannot work at synchronous speed. We will see that thing in a couple of examples. So anyway, so you can write the rotor speed in terms of slip and the synchronous speed as 1 minus s times ns. Okay, so if slip is 0.5, that means rotor is rotating half of the speed of the synchronous speed. If the slip is equal to 0, then that means rotor is rotating with the synchronous speed. Okay, then another important definition is the frequency of the induced rotor currents. Okay, so they are usually shown by Fr. So those, what happens to Fr when the rotor is stationary? Okay, if the rotor is stationary, so that means you are rotating those magnets. So all our system is basically like a transformer excited by some AC system. So you have some short circuit coils, so they are stationary, and you are applying a rotating MMF at Fs. So basically what you will see in the rotor is, for example, if you are applying 50 Hertz to the stator, and if rotor is not rotating, so you are holding with something, then if rotor is not moving, and if AC magnetic field, rotating magnetic field, is rotating at 50 Hertz, then you will see 50 Hertz induced voltage in the rotor bars, in the rotor windings, as if it is a stationary transformer. Okay, so the question is, what happens to Fr when the rotor is rotating at synchronous speed? Okay, so the question is, now somehow I'm rotating the the rotor at 50 Hertz, and the stator coils are also excited by 50 Hertz, so they are rotating 50 times a second, but our rotor is also rotating at 50 times a second. So from the rotor coils perspectives, so it is as if you are not seeing any AC magnetic field, but you are as if you are seeing a constant magnetic field. So you are as if seeing a DC excited winding. So as a result, if the rotor windings doesn't see any varying magnetic fields, then they don't create any induced voltage, and they don't have any currents, because again, in the squirrel cage induction motors, they are not excited by external fields, but they are working on the principle that the induced voltages, first you induce some voltage, then those induced voltage create some currents. So if you don't have any induced voltage, then you will not have any induced currents, and if you don't have any currents, then you will not have any torque at all. Okay, so again, it is kind of difficult concept, but you can think like of all relative speed. So if you are, for example, if you are on a train, okay, and if you are just standing on top of the train, and if the train is moving at 90 kilometers per hour, so if someone is looking to you from the station, so that will see that you are moving at 90 kilometers per hour. Okay, but somehow again 90 kilometers is not really realistic, but anyway, somehow if the train is moving at 90 kilometers per hour, but somehow you are running in the opposite direction with 90 kilometers per hour, then something in the station will see you as stationary. Okay, so we will have the same concept. So when thinking of the induced voltage frequencies, you need to think of all relative speeds and relative frequencies, and I will solve a simple example between that. Anyway, so if your rotor is rotating at synchronous speed, you will have no relative speed between the rotor and stator, so there will be no induced voltages. Okay, so again we can write Fr. Fr is the frequency of the induced rotor currents, can be written as S times the stator frequency. Okay, so again, what is the torque generated at synchronous speed? And if you don't have any varying magnetic field, you will not have any induced voltage and you will not have any currents, so that will create no torque. Okay, that is really important for induction motors. So when the slip is equal to 0, there will be no torque. Okay, so they are induction motors, therefore they are also called asynchronous motors. Okay, so we have basically two main classifications for AC motors: synchronous motors, as we have seen in the last weeks, and the asynchronous motors. In induction motors are asynchronous motors. They can run at every speed but not at the synchronous speed. Of course, you can connect some external torque, so you can rotate the rotor manually, but in a practical application, so induction motors have to run, if they are working as a motor, they have to run always slightly slower than the synchronous speed, so there have to be some non-zero slip to create some torque. Okay, so they are called asynchronous motors. So let me solve a really basic numeric example to cover what we discussed. Okay, so here we have a three-phase, 50 hertz 6-pole induction motor, and that is rotating with a slip of 5%. Sometimes slips can be given like as 5%, or it is also is equal to 0.05. So let's calculate the electrical synchronous spin in radian per second. So let me calculate it. So electrical, that is really simple. So we have 2p Fe, and it is 50 hertz, so it is 100 p radian per second. Okay, so then, and B, let's calculate the mechanical synchronous speed in RPM, and whenever there's mechanical speed, we need to think of the number of poles. Okay, so what you can do is, in order to have an synchronous, or it can be written as ns, so normally it is 50 hertz per second, so you can multiply it by 60, so revolutions per minute, but this is again the electrical, so in order to divide it, you need to in order to calculate the mechanical speed, you need to divide by the pole pair. So it is a 6-pole machine, so I need to divide by 6 over 3, so you have 3000 divided by 3, so it is 1000 rpm. Or again, you can use this formula that we have just discussed: 120 f divided by number of poles. Actually it is the same, so that's again 1000 rpm. Okay, then C is the actual speed in rpm. So slip is equal 0.05, so I can calculate the rotor speed as the synchronous speed times 1 minus s, so that means the slip is 0.05, so the rotor is rotating at 0.95 speed of the synchronous speed. Okay, so you have 1000 times 0.95, that is 950 rpm. Okay, then let's have a look at the frequency of the rotor current. So if the rotor is rotating at 950 rpm, okay, so you can think like the synchronous speed is like 50 hertz, and the rotor is rotating at 1 minus s times fs. Okay, so that is 47.5 hertz. So if the stator is rotating at 50 hertz, and again if the rotor is rotating, again not not mechanically, because we have a number of poles, but if you look everything from the electrical point of view, so what you can do, for example, if you have a permanent magnet in the rotor, and if you rotate it around 950 rpm, so the frequency of the induced voltage will be 47.5 hertz. Okay, so the difference between these two FR, the difference between these two will be 2.5 hertz. So if you happen to connect an oscilloscope to the rotor, okay, the short circuit bars, and if you measure the frequency of that current, you will see 2.5 hertz AC signal. So let me summarize it again. So the stator is excited by 50 hertz, okay, and it is a 6-pole machine, so mechanically the rotor is rotating at 950 rpm. And if you connect an oscilloscope to the rotor bars, you will see an AC signal at not 50 hertz, not 47.5 hertz, but the difference between these two, so you will see some current at 2.5 hertz. Okay.